In this video, we're going to look at another type of discrete random variable distribution, and this one's called the Poisson distribution. So unlike the binomial distribution, there are different conditions under which we would choose this distribution instead, but they're actually very similar to each other. And I'll put a link to a Khan Academy video that you could watch if you want to, which shows the parallels between the binomial distribution and the Poisson distribution and the derivation of the formula. I'm not actually going to go into the derivation of the formula in this video. What we will look at though is what is the Poisson distribution, under which circumstances would we use it, and what's the formula. And although I haven't mentioned it there, at the end of the video I'll also show you how the GDC can cut out a lot of the legwork and do the calculations for you, just like with the binomial distribution. And just like with the binomial distribution, you will get full marks in the exams just by using the right notation and then typing it into your calculator and writing down the final answer. You do not get any extra marks, or you're not required to write down the formula. But I will still show you what the formula is so you know where it comes from. So the Poisson distribution, as I said, is an example of a discrete probability distribution, and the times when we'll use it, the thing that we'll see is we'll be told the average number of events that might take place in a certain amount of time or space. So here's an example. The average number of people coming into a health centre per hour is 20. So I've been given an average, and then I want to work out a probability of, as in this case, what's the probability of more than 30 people coming in an hour. Another example, the number of emergency calls received by an ambulance station per hour is 20. What is the probability of less than 10 calls being received? Here's a series of conditions that we would have to follow. So discrete outcomes, the number of occurrences, so the number of times when we're looking at the probability, the number of times this thing could occur, whatever it is, the number of phone calls coming in, the number of people entering a queue, for example, we're going to assume could go from 0 to infinity. So that's the way that the distribution has been set out, even though we know in reality we wouldn't be able to have infinitely many occurrences in a given time interval. We're going to assume that each event is independent of others. And this is potentially the condition that is the one that is least likely to occur in a real life situation, which is the expected number of occurrences are constant throughout the experiment. If you imagine in reality, it's unlikely. For example, let's say we were talking about the number of cars that are going past a particular point for a particular point in time. That's unlikely to be constant. Throughout the course of a day, for example, there will be times of high volume of traffic, times of lower volume of traffic. So that's an assumption which perhaps in reality is not so likely to be true, but the Poisson distribution still allows you to then get a reasonable picture of what the true probability might be. And certainly for IB, M is what's used to denote the mean number of occurrences in the given interval. And it needs to be known, and it needs to be finite for us to be able to use it. Often you will look, if you look online, and actually in the past when I've used this, the Greek letter lambda is used for the mean number of occurrences. But as I say, for the IB examinations, an M is used. So if we meet these conditions, then we have a Poisson distribution which we can use to model our situation. And just like before, when we would often use a capital letter X to denote our distribution, we then need to say how it's distributed. So we say X is distributed by, and the PO stands for Poisson, and we just have to give one bit of information, which is what is the mean value. Unlike with the binomial distribution, when you wrote a B here, and then you said the number of trials and the probability of success. So whenever we're describing a distribution, we're just basically giving the key bits of information that are about this distribution. This is the formula that we use. So if X is modelled by the Poisson distribution with a mean of M, then the formula we can follow is the probability that X is equal to R. So the probability that the number of people entering a queue in a given time interval is let's say 3, is going to be equal to the mean to the power of R times e to the minus m minus of the mean divided by r factorial. So we'll look at a couple of examples then to actually utilise this. Along a stretch of motorway, breakdowns occur at an average rate of 2 per day. What is the probability that on a particular day there will be 3 breakdowns? So the formula we're going to look at, we've got a mean this time of 2, because we know that there's an average rate of 2 per day, and we're looking for having 3 breakdowns, so our R value is going to be 3. We need to define what x is, so also let x be the number of breakdowns in a day, and we need to say how x is distributed. It's distributed by the Poisson distribution with a mean of 2. We can then substitute the values into our formula, so the probability x is equal to 3 is the mean to the power of r times e to the minus m over r factorial, which in this case comes out as being 0.180 to 3 significant figures. Second example, so we're still on the same stretch of motorway. What is the probability that on a particular day there are less than 3 breakdowns? Now, when we see how to do this on the GDC, we'll be able to do cumulative probabilities, i.e. adding a number of probabilities together very, very quickly with just one entry into the calculator. But if we were to do this by hand, the only way we could do it is work out the probability that x is equal to 0, 1 and 2 and add them together, because obviously if there's less than 3 breakdowns, that means there's 0, 1 or 2 breakdowns. Less than 3 obviously is not including 3. If you did all the calculations for each of those individually, that's what it comes out as, and we then get 0.677. The last question we're going to have a look at is just changing the time interval that we're looking at. So what is the probability that there will be 20 breakdowns in a week? So we know the average rate is 2 per day, but if we're now looking at a time interval of a week, we need to obviously multiply this by 7, because there will be an average rate of 2 times 7, i.e. 14 breakdowns per week. So x is distributed by the Poisson distribution with a mean of 14. Stick all the values into the formula, and the probability comes out as being 0.0286 to 3 significant figures. And this again just brings me back to the comment made earlier about when we're allowed to use the Poisson distribution. We're talking about there being an even spread, an even distribution of when these breakdowns might occur. But actually in reality, there's unlikely over the course of a week to be a constant rate of traffic. There will be certain times when there are more cars on the road, and at those times the breakdowns are going to be more likely to occur. So in this situation, it would be unlikely in reality to fully meet the criteria of the Poisson distribution, and therefore we would be using this more as an approximation. Now let's have a look at how we can use the GDC to solve problems with the Poisson distribution. And as mentioned before, you can use this rather than having to use the formula. You get no extra credit by using the formula rather than just typing it directly into the GDC. Just make sure that you use the appropriate notation. So you establish what x is clearly, you state that it's a Poisson distribution, and you use the kind of notation such as probability x equals 3, for example, in part A. So let's have a look at how we can go about doing this. Again, very, very similar to what we were doing with the binomial distribution. So we'll go onto a calculator page, first of all, and we'll go through the same sort of options, probability, distributions, and we need to scroll right down to the bottom. To be honest with you, you can actually go up and you'll find it faster because it's literally the last ones here. Poisson PDF is for finding one individual probability. Poisson CDF is again the cumulative distribution function, so it will add multiple probabilities together in a range that you can specify. So for the first question that we were looking at, we were taking a situation where we were looking at the mean number of breakdowns in a day, which was said to be 2, and we wanted to work out what was the probability of there being 3 breakdowns in a day. So that's the x value. Click OK, and there it is calculated right for us. So that's the same result as we got previously when we were actually using the formula. If we then look at the next example, we're going to have a go at finding a cumulative distribution function this time round. So again, if I scroll down, we'll use CDF. Again, we have a mean of 2, and we're trying to work out the probability that the number of breakdowns is less than 3. The probability that x is less than 3, which is the probability that x is equal to 0, 1 or 2. So the lower bound is 0, the upper bound is 2. Remember, these bounds, it's inclusive of these bounds. So this is going from 0 to 2, including 0 and including 2. If we click OK, it's straight away added all those probabilities together and given us the final result. And again, that's fine. You don't need to break down this calculation. You can type that in and write that down on your exam script without any need for further working. If we look at the last example, we're trying to look at the probability of there being more than 5 breakdowns. So again, this is going to be Poisson CDF, but the difficulty here is, as I mentioned earlier in the video, the Poisson CDF, with the Poisson distribution, we assume that the number of outcomes can range from 0 to infinity. So if we're saying more than 5, we're basically saying 6 right up to infinity. And obviously that's not something we can actually directly type into the calculator. So rather than saying I'll work out the probability from 6 to infinity, we can do 1 minus the probability of being between 0 and 5. So we basically get rid of all the probabilities that we don't want, and obviously that will then work out the probabilities that we do want, i.e. 6 onwards. So we'll stick in a 1 minus, and just as a shortcut, rather than going through the menus again, I can just go into Poisson CDF, select that there, and the way this is working is it's got the mean as the first value, the lower bound, and the upper bound. So we wanted to change the upper bound to being a 5, and that will then do the calculation as 0.0166 to 3 significant figures.